Good morning or afternoon, depending on from where you're joining us today, and welcome to our webinar. My name's Keely, and I'm the editor of Fibre Systems. I'll be your moderator today. So let's dive into the topic. Our topic today is Beyond the Power Wall, photonic switching and CPO for AI. This is in line with AI clusters scaling to tens of thousands of GPUs, traditional electronic packet and switching hitting limits in terms of latency, power, cabling, density, and silicon photonics moving from lab to real deployment. In terms of why this matters, it's that we're getting to a maturity point with optical switching from prototyping to production, and from wavelength selective switching to all optical circuit switches. So the decisions are being made now about the next generation, how the next generation of AI gets built. So I'm very pleased to have two brilliant experts at the forefront of this transition joining me today. We have Ted Nicholas, Engineering Director for Data Center and Cloud Business at AFL. And we have Ana Gonzalez, VP for Business Development at iPRONICS. We hope you enjoy the webinar today. Feel free to submit your questions as we go. They'll be answered at the end, but that's no reason not to submit them early. So without further ado, I'm going to hand over to Ted. The floor's yours, Ted.
Hello, wherever you may be. I'm going to start off with just a sort of a quick overview presentation. So I'm going to share some slides, and let's see, we'll kind of walk through. So Ted Nicholas, Engineering Director in the Data Center Cloud Business Unit at AFL. Just a quick, let's see, a second to advance, maybe just a quick overview of who AFL is. So AFL is a fully owned subsidiary of Fujikura. So Fujikura has been a well-established company, headquartered out of Japan, global footprint, 50,000 employees, of which AFL is part. A long history of supplying products of different types, but currently the focus is really on four main operating units: telecom, power, automotive, and electronics. So AFL really feeds into the telecom and power piece. Okay, AFL itself is headquartered in the United States and North America, and has a footprint that complements the overall Fujikura footprint. Facilities in the United States, Mexico, and Canada, Europe, in the UK and Poland, and in Asia, China, Singapore, Australia, and India. So about 10,000 employees overall. Was founded in '84, so a little over 40 years ago, and really servicing four core markets. Okay, the data center business unit that I'm part of, a broadband unit, and energy. The data center unit that I am in, probably the best way to look at it is we're sort of a passive infrastructure supplier. Okay. Now, wanted to kind of put a little bit of a context, maybe from a market standpoint of driving towards a higher density and co-packaged optics. So this is some information provided from Light Counting. It's really focused on switch evolution and growing market demand going out to 2030. Probably the real key takeaway of this slide is that you can see a significant growth in the scale-out switches. Oh, is it not sharing? Apologize on that. Let me go back. Okay, let's try this again. Okay, and okay, is it sharing now?
Yes.
Okay, sorry about that. Well, here we can kind of hit off from this slide. And like I said, really kind of the market context, looking at a switch growth going out to 2030, looking out both scale up and scale out switches, and obviously significant increase. So just taking this as a general indicator of the increasing fiber demand and the growing demand for density. Okay. All right. Advance to the next slide. And just in the general, there's been a big debate exactly around scale up and then also when co-packaged optics will really come into full market acceptance. So you can kind of see the planning from Broadcom, Marvel, NVIDIA, at which point they see the need for the transition to co-packaged optics. Okay, NVIDIA is projecting obviously towards middle of next year, and then Broadcom and Marvel shortly thereafter, which means that a lot of the development work is ongoing right now. But this is really driven by power consumption, and we're approaching sort of a critical point where we need to reduce power in order to be able to meet the growing AI factory needs. Okay, so that's sort of, just sort of the market context of what's driving a lot of this development. Okay, going to really kind of transition a little bit more into kind of the technology piece, at least from a connectivity standpoint and a co-packaged optics standpoint. Okay, so I always reluctant to start with some definitions, but just for clarity, scaling up is really connecting GPUs or TPUs as the case may be, and there's going to be growing pressure as scale up starts including more and more racks, the need to improve this high density connectivity, the bandwidth, and improve the connectivity. Obviously, scaling up or connecting, multiple, basically AI nodes into larger clusters is going to continue as well as the AI models and their complexity increases. So really what this means overall it's going to put a lot of demands on the optical network that are continuing to progress. A need for a higher density connectivity, so that includes on the cable and fiber side, but also the connectors themselves. The demand for increased bandwidth obviously will still also push for the density from that standpoint. But as kind of mentioned earlier, we have to reduce the overall power consumption and reduce the latency in order to basically support the needs of the AI factories. Okay. Kind of transitioning to more of the specifics, and I've tried to kind of keep this relatively general. Okay, so when you start looking at kind of the backbone, fiber, and cable piece, you'll see a steady progression on single mode fibers. Obviously, I think 200 micron fibers, single core in adoption, but there's a push for potentially even smaller fibers, so you can drive smaller cable diameters to support all this interconnectivity. And I think kind of well known that ways to, if you want to decrease the size of the different cables, having sort of a central core size that with some sort of flexible ribbon. Okay, the example shown is what my company provides, spiderware ribbon, but there are a lot of other good solutions out in the market that help you decrease the size of these trunk cables. And another growing trend is the evaluation of multi-core fibers. Okay, the first sort of early trials are being done with 4-core multi-core fibers, where you'll have the fiber itself will be 125 micron outer diameter, but it will have 3 cores, roughly spaced about 40 microns apart, and this helps solve some of the density issues. Okay, and there are other multi-core fibers that are available in the same sort of fiber footprint, 7-core, 12 cores that will continue to be commercialized in the future. All right, so with the fiber standpoint, whether single mode or multi-core, part of it drives down to smaller diameter cables, okay? And there's a lot of, with the increased connectivity in the cable trays, there will be a lot more pressure to try to reduce the diameter of the interconnects into smaller cable forms, okay? I just wanted to give a quick kind of just motivation to show what multi-core fibers could do for you. So if you looking at a 576 fiber cable, which is pretty common to connect to like an AI rack, that you could achieve the same connectivity with the 144 cable with 4 cores, so which 4-core fiber, which will give you the 576 cores, but a much smaller cable footprint. Okay. Now there are challenges associated with using multi-core fiber, but these are being solved by the industry currently. Okay. And wanted to kind of switch over a little bit to talk about the high density connectivity, the multi-fiber connectivity that's kind of in use currently. So you could really break this down into, or at least how I look at it, as kind of epoxy polish connectors and kind of an emerging marketplace of lens connectors. Okay. And some of this is also driven to facilitate the connectivity that exists within the transceivers. So some of the examples that are going through that a workhorse in the data center market for a long time has been the MPO, but there's a transition to the MMC connectors and the SNMT. So the MMC connector developed by US Connect and has been adopted by a number of different people, presents a very small form factor in sort of a miniaturized kind of MT style ferrule, in a similar type of solution offered by Senko in the SNMT. So this allows us to, at least from a fiber management standpoint in transceivers, to connect essentially more fibers into a smaller footprint. An additional emerging technology is the expanded beam connectors. Okay, and the one that's probably been out on the market a little longer, that's has a good performance in the single mode space is 3M's EBO connector, and US Connect is following with its PTMT, which I believe will be commercially available early next year. So the value of those connectors are expanded beam, although the loss may be marginally higher than what you see in the traditional epoxy polish. It allows for turn-ups faster of connecting because of maybe a lower need to clean. Okay. Lastly, kind of with the higher density that you're seeing, you'll have a push for what I'll call gang connectors, to try to tie multiple connectors together to plug into panels to have the smallest possible footprint. It's just an example of that type of connector is shown kind of in the lower panel, where you have, in this case, it's just showing 15 ferrules in a front panel connector, and you have a connector that could plug in. This particular solution was shown with an older lensed version, but the general idea is there that you're achieving a very high level of connectivity in the smallest possible footprint to facilitate the turn up of facilities. And I think you'll also see on the market a number of kind of mass insertion approaches for gang connectors to be able to help with the turn up of connectivity at panels or top of rack. Okay. All right. Just sort of transitioning to kind of the co-packaged optics idea. Okay. And the primary motivation around that is with the increasing bandwidth, but also reducing power consumption. Okay. So the simplified schematics are on the side are showing sort of the traditional pluggable transceivers, okay, where the fiber will come in. There will be some sort of a fiber array unit that will attach to the optical engine, potentially going through some sort of a DSP made to the receptacle on the board, and then ultimately go to the ASIC for whatever application. It's sort of the next evolution is onboard optics, where essentially the optical engine is being moved to kind of the main board. So more of a direct connectivity. And then sort of the longer term evolution will be around co-packaged optics, where there will be the connectivity at the front panel. And then the fiber array unit would connect to a more of a silicon photonics element that will be on the same board as the ASIC, and that sort of presents the shortest, most direct connection. Okay. From what I'm seeing, and this is just sort of general, the pluggables are very strong, going up to 400 and 800 gig. You're starting to see As you get into 800 gig and 1.6, implementation of some of the onboard optics and the co-packaged optics is moving into some of the higher data rates. I mean, that's just sort of a general observation on my part. In really driving what the change is that if you can start driving the optical electrical conversion closer to the ASIC, you're going to improve your latency. You're also going to improve your signal quality. And a big piece of that is if you can eliminate the DSP, the digital signal processing, you can reduce the power consumption. Okay, so main drivers that way, just to sort of tie it together and sort of set the stage for some of the Q&A part. A lot of the solution implementation is around improving density. So this could be around with the optical fiber and the cable constructions, but it also dovetails with the connectors, okay? And the last piece is the evolution of co-packaged optics that's in the transceivers and certain piece of equipment. So at this point, I'll stop sharing and I can turn everything over to Anna, and she can proceed with her presentation. Thank you.
Thank you, Ted. That was really insightful. It's looking at some of the real life, the density challenges. It kind of brings to life exactly what's going on. So thank you very much. And as Ted said, we're now going to hand over to Anna. So Anna, the floor's yours.
Okay, so I'm going to share my screen. Let's make sure that I'm sharing a screen.
Yeah, you did better than I did.
You are sharing. Thank you.
Thank you, Ted. Okay, so then hello everybody. Happy to be here to present our work on silicon photonics optical circuit switches. So now for the next 20 minutes, I'm going to, well, first, to describe the current momentum that photonics is experiencing in the industry, and in special what is happening in the OCS field. And then we will go for a deep dive on our work on the development of high density integration silicon photonic chips and how we have used this technology to develop an OCS for scale-up applications. Okay, so let me start explaining to you how photonics has become a key enabling technology for AI using this screenshot from Jensen's keynote at GTC 2026 as a background. So around 3 years ago, data centers were already close to a bandwidth bottleneck, but kind of keeping up because of the nature of data center communications. And I mean low bandwidth, high entropy, so yes. And then the AI boom happened, and AI communications are presenting different patterns. So communication are less frequent, so less entropy, but they require all the bandwidth. And this has created a massive pressure on AI cluster architectures. And this is the real bottleneck that is happening now. So yes, copper interconnects are reaching a fundamental limit in bandwidth, distance, power, and now NVIDIA thinks that scaling more GPUs within the same domain is very expensive if you are using copper. So in March this year, Jensen summarized it like scale up moves to optics. So he says, we will use copper in the scale up? Yes. We will use optics? Also yes. So the takeaway is AI clusters need more capacity. Copper is still in the picture, but optics is the only way to scale up efficiently. Okay, so how OCS fits in this picture? So Jensen didn't mention OCS at the GTC, right? And you can just connect racks using fiber optics. But it happened that NVIDIA GTC this year was at the same week than OFC. And at OFC, one day after Jensen talk, Craig Thompson from NVIDIA gave this presentation on optical circuit switching based on previous investigations of NVIDIA. I borrowed this slide from his presentation. Wait. Yes. to show you where NVIDIA envisions this coexistence of electrical packet switches and OCS. The advantages are the possibility of reconfiguring topologies and increased bandwidth availability. The main positions in the network that were explained in this presentation are scale across here, where in this case OCS has been already used, especially MEMS-based OCS. This is used to connect different clusters inside the same campus. Regarding scale out, this connects the different GPU domains, and Google has already deployed OCS in the scale out very successfully. Also, we can find other works in the literature talking about how to use OCS switches to overcome failure, and I will show something next. And finally, the scale up, that is what Jensen was mentioning. Electrical packet switching and OCS will coexist in this. This is going to work by keeping the NV switch inside the rack and then the racks connected optically. And this is how NVIDIA will be able to scale the domain to 576 GPUs and beyond. Okay, so here I just wanted to mention this previous work from NVIDIA focusing on failure resilience for AI applications, especially in large networks. In this network, they are demonstrated that by adding an OCS between the different layers in the scale-out, it is possible to rewire the network by reconfiguring this topology, right? And then you can avoid the workloads to crash when an element fails. So this is done through the control plane. So OCS doesn't work reading packets. It is controlled by software. In this case, this works is using a MEMS OCS. And let me explain here that a MEMS-based OCS works by moving micromirrors. So it's free space optics, right? It means that it's kind of a bulky device. It has movable parts, so intrinsic reliability is not so great, right? And it is usually associated to a higher cost than when we compare with silicon photonics. Just to finalize this slide, to say that this work comes from Paraskeva's group in Athens, and I will encourage curious readers to check the work of this group on OCS because they have multiple articles. Okay, but we came here to talk about the scale-up. This is the last slide that I borrowed from Craig's presentation, and here they are explaining about what are the characteristics that an OCS should have for an effective deployment. To summarize, they highlight here the importance of wide bandwidth operations and link quality. And here the focus is on the form factor because, well, many OCS will be required and they will need to be small. And then regarding reliability, they are requesting less components. So again, integration capabilities of the technology that will be deployed and also, of course, the cost will be very important. So when reading these requests, it looks to me that silicon photonics is better positioned than MEMS in form factor, reliability, and cost, at least. Okay, so now I plan to explain to you about the silicon photonics OCS that we are developing. So here, happy to introduce you the principal actor of the show. We started in 2019 developing programmable silicon photonics building blocks, and this is our main development. This is a 2 input, 2 output multi-mode interferometer, silicon photonics, controlled by applying small currents to a very precise thermo-optical phase shifter. And there are mainly 3 states for this configuration. The cross state, the bar state, and also the tunable coupler. Yes, we control this phase, we choose one of these phases through small currents that go through nanometer-sized copper pillars using the software, the application programming interface. Then we put 2,000 of these building blocks together in a mesh arrangement with other building blocks. And we electrically connect through 8,000 of the copper pillars. We integrate silicon germanium photodetectors everywhere, in the chip inputs, outputs, before the optical amplification, because we also add optical amplification as well. Silicon photonics is kind of lossy, so we are compensating for losses with the optical amplification. And this is how we have developed our 1U rack size optical circuit switch. It's lossless. Even we can provide some gain control if required. It provides telemetry and it's scalable in radix. It has been designed for the different layers of the data center. I'm going to show later how we get a very flat spectral response in the entire O-band. So the device is going to be compatible with the different optical formats such as DR and FR. Yes, and this is possible because the design of the photonic chip, because this is what we do the best. So at iPRONICS, we design state-of-the-art high-density photonic integrated circuits. We are now shipping to the customers our 32-port switch. It already contains 2,000 basic building blocks, also 4,000 actuators. And our aim is to double the number of components every year. So we have achieved it already with the 164. This chip already contains double components, is double radix, and also we are now designing the 128, doubling again the radix. And we have in progress other solutions that in the future are going to allow us to scale the radix beyond the 1000 when it's required. We will be able to do this. And here you can see a sketch of the device. The front panel now has these MPO connectors, but we are planning the 164 will have LC connectors next year. And you can see here, well, this is the sketch of the device. So we have an FPGA, the swappable power units, and the disaggregated optical amplifiers that are there at the back. And some details on the silicon photonic chip. Here you can see the 132 chip details with the photonic switching matrix, edge couplers, the polarization controllers, photodetectors. You can also see here the 164 with double components, but you can see almost the same form factor. Okay, so very nice chips, right? But what about the performance? So, yes, losses is the number one optimization parameter of our device. Even if we add optical amplification, it has a cost. The less we amplify, the less impact in the signal-to-noise ratio. So less impact in the bit error rate of the signal, right? Here I'm showing to you an overview of all the efforts in the last 2 years at iPRONICS on developing high-performance silicon photonics building blocks for data center applications. And well, let's start here with the 3dB splitters. So this graph represents the insertion loss here in the entire range of wavelengths of interest from the 1270 to 1330 nanometers, or also called the O-band, right? Which is the chosen one in the layers of the data center. So the black line here is the performance of from the building block that was available in the PDK of the foundry. As you can see, very centered in the central wavelength in the 1330. So then we had to iterate and develop different versions to be able to get a building block that was having a very flat response in the entire O-band. And you can see here we got it with this green line. Yes, the response is very flat and it makes this building block compatible with the different optical operations. And then also you have here the example for the monolayer crossings. Again, the black line is the PDK of the foundry, and then we were through iterations, design, fabrication, testing, redesign, fabrication again, we were able to reach, you can see very low insertion loss for the last version of this building block. And with these state-of-the-art building blocks, we have built and commercialized the first silicon photonics optical circuit switch. Solid state, CMOS compatible, we plan to reach the lowest cost per port. We incorporate gain controlled links disaggregated today, but maybe one day we can incorporate them on chip by hybrid integration or another method. And because it's silicon photonics, we can incorporate photodetectors that in DC language means telemetry, right? Connected to the SDN through our application programming interface. It has advantages. Silicon photonics has advantages when compared with MEMS, especially for this type of applications. Mainly, as we already mentioned, reliability, form factor, but also reconfiguration speed. So silicon photonics can reconfigure much faster. So it's ready to scale speed, reconfiguration speed when the application requires it. Okay, so what about power consumption? Here I want to show you a comparison of the estimated power consumption of our 64 radix device. So you can see this is the blue line. In this case, that will be always less than 100 watts. And then you can compare with the power consumption of a future 1.6 terabyte per port electrical packet switch. In electrical switches, the power consumption scales with the data rate. So here in this column, the port is the black part. But in addition, it needs a transceiver per each electro-optical conversion, which is the gray part of the pillar. But when you use an optical circuit switch, you don't use transceivers, right? So you get this amazing reduction of energy, of power consumption, especially in higher data rates like this 1.6 tera. Okay, and what about the spectral response? Yes, you can see the flat spectral response after amplification. You can see dashed lines are the FR wavelengths, WDM here in the middle, and yes, you can also see crosstalk with other ports that it was even difficult to measure. And yes, regarding the bit error rate degradation, the link stability, the degradation is always less than 1 decade for all type of formats. And we also design fabrication processes for volume production. We are talking about thousands of copper pillars per chip that need to be able to match and connect so we can have these all-to-all optical switches. And also then we are talking about fiber to the PIC, so optical coupling for fibers array of 32, 64, 128. So for this, we are partnering with tier 1 service providers. An example is Fibre. You can see here this fantastic picture of the flip chip bonding performed by them. Okay, and I would like to end with the software layer. So as I said, an OCS is controlled by software. So the software that we have developed at iPRONICS for the control and telemetry, this is very standard-based. We use GNMI and Netcom for this reconfiguration and streaming telemetry. We can do set and get operations and subscribe for telemetry. And as I explained it, each port is tied to monitored optical power. So it has photodetectors. So, and each connection is tracked with a unique connection ID. In order to align with the other OCS vendors, with models, interfaces, we are leading together with Lumentum the OCS standardization initiative within the networking project in the OCP, in the Open Compute project. And we are also working with other partners in the higher software layers, for example, developing orchestrators and controllers to be able to benchmark our technology against current solutions. And as conclusion, we have developed a silicon photonics optical circuit switch compatible with current and future standards, based on reliable state technology, data rate independent, very compact form factor with gain and telemetry capabilities and fast reconfiguration time. And we think this technology has the potential to be widely deployed in scale-up networks. Thank you very much.
Thank you ever so much, Anna. That was really fascinating stuff. It was really interesting to hear what you guys are developing. It's the future's definitely exciting, and it's all starting now. So we are now moving on to our question and answer session. There's still time for you to send questions in, so please feel free to do so. While we're just waiting, I will ask a quick question. What would you both say is maybe the biggest myth about optical switching that you'd like to see dispelled? Who'd like to take that one first?
So you are asking for the biggest myth. I will say the biggest kind of bottleneck or concern about optical circuit switching is about how you are going to control the optical circuit switch, kind of the software part, because it's very different from the EPS. And we already identified this bottleneck soon enough, and this is why we started working with the different initiatives like this, the Open Compute project, where we are aligned with, we are co-leading this group together with Momentum, but we have Meta, Google, Microsoft, they're collaborating. So yes, and also to develop the different orchestrators that now are not working with the APS, now need to orchestrate through the OCS. So we are interested in this type of demos and benchmarks to be able to demonstrate that it's not really a bottleneck, it's just a software development that needs to be done. And after this, yes, you can control the OCS.
Okay, fantastic. Ted, same question for you.
I don't know if I can certainly not provide as much insight that Anna can provide, but since but at least for me, the transition would be essentially the myths around maybe getting the high level of reliability that would be expected in the cost. And I think what Anna presented kind of shows that companies like hers are addressing those issues. So
fantastic, thank you. So we've had a question come in for Anna. Anna, is there any thermal output analysis done? Somebody would like to know. Would you like to enlighten us on that one?
Yes, I assume they are asking for what is the thermal crosstalk, and if one of the thermo-optical phase shifters in one of the building blocks affects the one that is next to it. And it doesn't affect. Yes, we did all the thermal analysis. And I also have to say that maybe 4 years ago, the energy that was required for moving this to change the phase of this actuator was very high. But then, because of optimizations in the foundry, in commercial silicon photonics foundries, now the power consumption was reduced like 50 times. So everything that was regarding thermal crosstalk was completely disappeared. So no, we don't have any thermal crosstalk in the chip.
Fantastic. And another one come in. Do you use SOAs for your OCS to help mitigate inherent losses?
Yes, this is why we need to use an optical amplifier. So when we transmit through the silicon photonics chip, we get some dB of losses, and then we are using this optical amplification to compensate. We only work in the linear range of the optical amplifier. We can amplify certain losses. And in this linear region, we don't observe noise effects, neither acid effects. So yes, the impact in the noise, even if there is some impact in the noise, at the end is an active element, it's very, very low.
Perfect. Thank you ever so much. We've had another one come in this time about CPO. So the adoption of MCF, the CPO, are there evaluations with customers in progress? And what, if any, are there barriers to adoption?
Okay,
Ted, I'm going to hand over to you for that one.
sure. So there are some, I can't obviously give the specifics, but there are some customer field trials going on with some hyperscales for four-core, multi-core evaluation. And I think a lot of people have seen that there's an ecosystem of transceivers that are available for direct link of multi-core fiber. I think as basically the technology develops, when it comes down from a challenge standpoint, maybe from the overall adoptions, that there's a limited number of multi-core fiber manufacturers. Okay,
Yeah.
so there has to be setting up the cable. The alignment process within the connectivity is more complicated. You obviously have to have a precise positioning of the fibers, relative to some sort of keyway for connection, so that you can get the polarity interconnect part of it is obviously more complicated because you've added the four cores in addition to that piece. When it comes down to maybe the CPO piece, obviously a solution has been done with the transceivers. I think for sort of future adoption, when it comes down to the interface with silicon photonics, I think the first path is really for maybe some vertical coupling solutions, and then develop that modeling so that can be done with the foundries. I think that will be probably the first implementation from a larger scale, so you can stay away from using FIFOs. And then maybe a little later on, some of the edge connect solutions will be going through. So kind of multiple parts from the overall adoption to be able to go through. So I think the industry is still evaluating, are we getting the benefits for some of the challenges, but I think it's likely.
Okay, brilliant. Thank you ever so much. And a question from me actually for both of you, if that's okay. In terms of the kind of standards and interoperability, everything's moving at quite a fast pace at the moment. We're seeing new connectors, fiber types, switching architectures, all kind of emerging and in different sort of states of emerging at once. Do you think there's an issue? Should we be concerned as an industry in terms of fragmentation versus innovation, or do you think that that's kind of covered off? Ted, while you're here, do you want to take that one first? Is that
Sure, I'll take a first stab at it. So obviously the technology is moving very quickly. So there are some MSAs like SDM4 has started to address some of the multi-core fiber. I know APC, Advanced Photonics Coalition, is working on tying together a number of different points in the industry to try to come up with standards around co-packaged optics, and a set of that is multi-core fiber. I know IEEE is looking at it. I know personally I'm involved in APC, and I know there's been efforts to liaise with the other groups to try to get more coordination of the technology. So obviously there's a big challenge with that when you have independent standards bodies, but there does appear to be a strong concerted effort to try to coordinate.
Brilliant, thank you. Anna, can I take this one to you now?
Yes, just to add to Ted's comments, that at least in what optical circuit switching, what we see is the leadership of the hyperscalers together with NVIDIA, right? So somehow they are establishing what are the standards, right? With even calling them standards. So then we follow the lead, right? And at the same time trying to standardize interfaces, software and hardware interfaces, as I was commenting, of our work in the OCP.
Okay, brilliant. Thank you. So I'm interested to know, one for both of you, is there anything that's maybe surprised you about deployment readiness in the past 12 months? Anna, while you're here, is that okay? Can I take this one to you? Is there anything that you've kind of seen that's maybe you've gone, oh, wasn't expecting that?
That yes, well, it's not that we were wishing it, right?
Yeah,
Expecting it, it's happening fast, right? So
yeah,
now we see movements in the industry. So not only the ones that I presenting, announcing finally how optics is getting into the scale up, but also big investments, right? Trying to secure the supply chain that will make this possible.
yeah,
So this all happened since the beginning of the year, and well, still there is an exciting road for optical circuit switching and photonics in general in the next 2 years.
yeah, absolutely. Thank you ever so much. And Ted, same question?
Probably what surprised me is how rapidly it's moving and the rate at which it's scaling. Okay, at least at my end of the ecosystem, the demands on supplying fiber, cable, connectors, the number of suppliers that need to come online to meet the demand. That's probably been the biggest surprise, and I've been encouraged how that sort of demand is being met and how it's driving a faster acceleration of the technology.
Amazing. Thank you ever so much. We've had another question come in for you, Anna. And the question is, how robust are the heaters on the PICs? The switches can be on for days on the servers. Do they drift due to thermal effects on the material? And if yes, are they auto-corrective?
Okay, so I understand the first part of the question is about reliability, right? So what we have here is a new technology. However, we had a product before. So we have already a product in the market that have been working in customer hands for more than 3 years now. So the heaters are very robust because the energy that we are sending them to control the phase is very small. So this is why they can work continuously. However, reliability testing is now going on. Um, and then regarding drift due to thermal effects on the material, no, we don't have this. This is photonics, right? So the thermally, it's much more stable than when we are talking about electronics. But I understand that everyone asks this because this is what happens in data centers. But this is photonics, so this is new generation technology.
Absolutely. Yeah. Fantastic. Thank you. Thanks ever so much. Let me just have a look. Looks like we may have another couple of questions just come in now. Bear with me. In the meantime, I'm going to ask, Anna, you mentioned compatibility with ZR and ZR Plus, and Ted, you showed multiple connects to standards. Who's driving the standards? Is it the market or is it the technology? And what's the kind of pace between the two?
It's both. So we are following IEEE standards to be able to design the chip following the right input power, the required output power. So IEEE standards is a good initiative, OIF as well. And again, this is led by the big companies, right? Such as the hyperscalers, but also the big data center vendors. And yes, we take the documents and we try to design the device that is compatible with the industry.
Brilliant, thank you. This is a good question for both of you, actually. Are fiber manufacturers, chip manufacturers, working in collaboration to meet the demands of the scale up and scale out requirements?
I guess I can start. At least from the fiber standpoint, I think globally, fiber manufacturers are trying to scale their capabilities, right?
Yeah,
And add. It takes a long time to add other drawing towers and things like that. So we're definitely in a constrained market state. Okay. But also related to this, there is still some level of innovation. Example,
yeah,
multi-core fibers, maybe developments that are happening with hollow core fiber to also meet some of the future needs. So definitely there is that work that's going on to be able to go through, to be able to use when you move beyond the kind of conventional single core fibers, you certainly have to have a lot of coordination on the PIC side to be able to use it and standardization. So it's kind of, I think both are kind of happening.
thank you ever so much. Anna, do you want to weigh in on this one as well?
Yes, from the point of view of silicon photonic chips, we have a great example of this with TSMC, right? That is collaborating with NVIDIA to develop the COPA process for the co-packaged optics. So yes, this is a clear alignment to be able to cover the needs of in the future needs of this industry. To have TSMC working on silicon photonics is great news for all the community, and we hope one day as well to use their foundries capabilities. Why not?
Fantastic. Thank you ever so much. If we don't have any more questions, then we are coming to the end of our webinar today. I just want to say thank you so much again, Anna and Ted. It's been an absolute pleasure talking to you. It's been so interesting and I've really enjoyed it. So thank you. Thank you to everyone who's tuned in today. If you would like to watch it again, or if you know anyone that would like to watch the webinar, it's going to be available on the Fibre Systems website for the next 12 months. And that's www.fibre, UK spelling fibre, systems.co.uk. So, yeah, it just leaves me to say thank you very much once again, Anna and Ted. Thank you very much to our production team and David working in the background to help us bring you this webinar. And thank you very much to our sponsors, to AFL and iPRONICS. And thank you from me to everyone for joining us. See you at the next one. Bye-bye.
Thank you. Bye.
Thank you. Bye-bye.